Okay, so this is section 15.7b. We're still talking about the idea of triple integrals. And one of the things I want to talk about in this particular section is really more of the setup of the integral rather than the solutions, because given the fact that we have a triple integral, it means we've got three things varying. There are multiple different ways that these things could be set up, and being able to figure out the different setups is going to be really important as far as being able to figure out which way is going to be the best or most convenient way to solve the problem. So let's talk about all the different possibilities. If you have a function of x, y, and z, there are going to be 6 different possibilities, 6 different ways that you can set these things up. So, for example, because I've got x, y, and z, I could do dx, dy, dz. I could also do dx and then switch the last two, dz, dy. Or I could start off with dy instead, and then I could do dx and then dz, or again start off with dy and then do dz, dx. Or lastly, we could start off with dz and then do dx, dy, or dz, dy, dx. So those are your 6 possibilities. So depending on what you think is going to be the best way to solve the problem might be how you determine which one of those 6 is going to be the one that you're going to pick. In our case, we're going to run through how to set it up for all of them in a lot of these problems. So the setup is going to be the important thing. This is probably going to be a 3-video lesson, probably these first 2 examples in the first video, and then we'll see how it goes from there. But I really want to spend some time because it's very, very visual, showing you how to think about and how to try and set these things up. So a couple things. The last 2 variables, the outer 2 variables, so in this case, the outer 2 variables, the last 2, those are basically going to be your 2-dimensional projection. So it's going to be into that plane. For example, in the top one, it's going to be a projection in 2 dimensions into the dy dz plane. And that's how you're going to figure out your bounds for the y and the z in that case. The x is going to go from a function up to a function. Now the function could be a constant, but it could also have y's and z's in it. So your innermost piece, which is going to be the first piece right here, like that one right there would be the innermost piece. X can vary from any combinations of y's and z's, because you're still going to have to take integrals or antiderivatives with respect to y and z at some point. The second piece, which is part of your domain, is going to depend on whether your 2-dimensional projection you do as a type 1 or type 2, but ultimately what you want to think about is y can have the variable z in it. It cannot have the variable x in it because you're no longer going to be taking an antiderivative with respect to x. So your bounds could be constants, or they could have terms of z. And then the last piece, the outermost piece, must be constants. Otherwise, you're going to have variables left over, and that's not going to give you anything. So you kind of want to think about it in that way. The other thing we need to be able to do is we need to be able to think about what these things look like both 3-dimensionally and 2-dimensionally if you're doing the projections. So this is where really knowing your quadric surfaces and quadric surfaces is going to be very beneficial. All right, so let's start off with the first one. E is going to be the solid bounded by the given surfaces. X squared plus z squared equals 4, y equals 0, and y equals 6. So hopefully you recognize x squared plus z squared equals 4 as being a circular cylinder. Because there is no y, we know that this thing is going to vary around the y-axis. So if we sketch the three-dimensional shape of this thing, again, it's going to be a cylinder revolved around the y-axis, and according to my last bounds there, it's only going to go from y equals 0 to y equals 6. So it should really look something like, oh, that was a horrible circle. It should really look something like this. It wasn't much better. Stay parallel if you can to the y-axis, and then draw yourself another circle at the end. That's just a good sketch to be able to figure out what this thing looks like three-dimensionally. So there's 0 and there's 6. Okay, so now what we have to determine is which one of these are we going to use? Well, we're going to set up all 6 of them. Okay, we're going to do that for every piece. I think probably the easiest one to start with, because the fact that they gave us y is going to vary from 0 to 6, is to probably let, no, it doesn't matter. It really doesn't make any difference. I was going to say we could let y be on the outside, but it doesn't matter. As a matter of fact, what I want to do is I want to look at this one. So let's say you're standing over here. We're standing at the end of this y-axis thing. We are looking straight at that piece right there. If you're standing on the y-axis and you're looking straight at that piece, what you're going to see basically is a circle projected back into the xz plane. So really what I want to do is, the first thing is I want to look at what is the two-dimensional projection into the xz plane. Well, it's going to look like a circle. And it should look like a circle with a radius of 2, because that's what x squared plus z squared equals 4 would look like. So that's going to be a circle with a radius of 2. So since that's my projection, that's my two-dimensional projection, my y values are going to actually be my innermost piece. So the first one I'm going to do is I'm going to do dy and then something. So let's go ahead and set up our triple integral. Leave a little space just so you can write your bounds in there of whatever our function is. I don't think we actually gave us a function. No, it just said a function of x, y, and z. So I'm just going to write f to keep it short right now, but it's a function of x, y, and z. So dy is going to be my innermost piece. Well, y is going to vary from 0 to 6. That one's pretty obvious because it literally gives that to us in the equation. To figure out now my other two methods, I can either make this a type 1, and we're not going to talk about switching it to polar yet, although you could do that in this case, obviously. But we could do this as a type 1. So the z values would vary from the bottom of the circle to the top of the circle. And then the x values would vary from number to number. So let's do it that way. Let's do a type 1. So that means that z is going to come first. So it would be dz. And then dx. So z is going to vary from the bottom of the circle to the top of the circle. So let's see. If we solve that thing for z, you would get that z squared equals 4 minus x squared, or z is going to be the plus or minus square root of 4 minus x squared. So the minus of that's going to be the bottom of the circle, and the plus of that's going to be the top of the circle. So the minus square root of 4 minus x squared up to the positive square root of 4 minus x squared. That's how z is going to vary. And then x is just going to go from, it looks like, -2 to +2, since it's a circle with a radius 2. So in this case, like I said, your y does not have to have variables in it. It doesn't have to have x's and z's. All of these could have constants depending on what it is that we're doing. But the inner one is the only one that can have both variables x and z in it. It didn't have either one in this case. The next one can only have an x in it in this case, because z can only vary from a constant to a constant, or some kind of a combination of a constant to something with x's in it, because x is the outer one. So that's the only thing that I can take the antiderivative with when I get to the last integral, is something with x's in it. So this would be the first of the 6. All right. The easiest thing to do, well, if you're writing these things out, is to literally start off the exact same way, having the inner one stay y. Okay, that's going to be 0 to 6. Now the only thing we're going to change is we're going to change it to be dx dz, which just means that instead of doing a type 1 on our domain, we're now going to do a type 2. And a type 2 means that x is going to vary from left to right, and then z would vary from a constant to a constant. So in order for x to vary from left to right in terms of z, we have to solve the original equation in terms of x, which is actually going to give us exactly the same thing as it did for z, just with the z variable inside the parentheses instead. And you can go ahead and solve that if you're not sure. So then x is going to go from negative square root of 4 minus z squared to the positive 4 minus z squared. And then z is going to vary from negative 2 to 2. So these two look almost exactly the same. All right, hopefully that makes some sense. All right, so what I'm going to do is, because I left a blank page here, I'm going to go to the next page. I'm going to re-sketch the three-dimensional figure, and then we're going to move on to the next set. So let's see, it was from 0 to 6, something like that. All right, so we've done one now where we stood on the end of the y-axis and looked at this thing as a projection down into the xz plane. Well, now instead, we're going to stand over here, someplace flat on the xy plane. If you were to kind of stand in the center of this thing and you turn it to the side, what you should see, and I should probably make this a little bit longer because this is going to be the zy axis, what you should see looks like a rectangle. It would just look flat like a rectangle, where this out here would be 6 units, and then this over here would be 0. That's what you should see if you were standing at the red X. Okay, so since we are talking about the YZ plane in this case being the two-dimensional projection, that means X is going to be our innermost function. So when I go to set up the integral, again, do a triple integral of f, we're going to put x on the inside part. So the question is, what does x vary from? Well, this is going to be a little bit harder to see, but x varies from the back side of this cylinder to this side of the cylinder. Okay, and then we can actually go back and take a look at the function of the cylinder, which was x squared plus z squared equals 4. I should probably copy that up here. X squared plus z squared equals 4. So that means x, if we solve this thing for x, is going to vary from the plus or minus 4 minus z squared, just solving that for x. So x is going to go from the minus square root of 4 minus z squared to the positive square root of 4 minus z squared. Okay, and then once you have that one done, because again, x can vary from anything that's got z's and y's in it. In this case, there's no y's, but that's fine, doesn't have to have it. Now we have to decide, are we going to do a dy dz or a dz dy? And again, that comes from your two-dimensional projection. So if you wanted to do a type 1, that means z is going to vary from function to function, y is going to go from constant to constant. So if we do this as a dz dy, z is going to go from the bottom of the function to the top of the function. Now you have to be careful here, because now this is a two-dimensional projection. This bottom piece right here is associated with the value y equals -2. So these are actually all going to be constants. It's actually quite nice to do it this way, because that's just a horizontal line at y equals 2. That's all you see. So that means that z is going to vary from -2 to +2. And then y is simply going to go from constant to constant, which is 0 to 6 along the y-axis there. And that would be the third of our types. Okay, then obviously we could take and do this as a type 2, which would go this direction, in which case y would have to go from function to function, and then z would have to go from constant to constant. It just so happens that in this case, the z is also just going to be constants because these are two vertical lines that z is going to vary from. So let's go ahead and write up our fourth one. Again, we are going to keep x as the inner one for these two. So it's still going to go from the same value for x. That doesn't change. And then we're going to change this to dy dz. Oops, probably want to keep that up there so we can see it. So y this time is going to vary from 0 to 6 first, and then z goes from -2 to +2. So because of the fact that this thing formed a rectangle, really it made it easy because they were just constant bounds in the last two. All right, so that's 4 ways. The other way that we could see it, and I'm going to kind of keep it from this original drawing, is that we could be standing basically, or floating, I guess you would probably be best to say, up above somewhere and looking straight down on this thing. And if we're looking straight down on it, we're looking into the xy plane. So the xy plane in this case is going to be our domain. So we'll sketch what it looks like in the xy plane. Here's x, here's y, and if you're looking straight above this thing into the xy plane, it looks like it's going to be a rectangle, which is 2 units on either side of the y-axis. So our sketch would look something like this. And obviously these are not drawn to scale, but I'm doing my best. And then that's 6 up there. So then all we have to figure out, because we know we're now the z is going to be the innermost integral of f. So we're going to do dz first. So z, in this case, varies from what would be, it's probably easiest to draw this one out here, from the bottom of this circle up to the top of the circle. And we have the formula that we have up here, which we can solve that for z. So we knew that z is going to go from the plus or minus square root of 4 minus x squared. So z is going to vary from the plus or minus square root of 4 minus x squared. Oh, yeah, we're back here with the domain. And then depending on whether we do this as dy dx or dx dy is going to depend on which way you put your constants, because they are all going to be constants here. So if we do this as a type 1, then we're going to vary with y first. So dy and then dx. So y is going to go from a function to a function, which is 0 to 6 in this case. And then x will go from -2 to +2. And then we're going to repeat this process for our 6th and final one, again keeping z as the inside, so it's going to be the same bounds, but then changing it to a type 2, which is going to be dx and then dy, which means that it would go this direction. So x is going to vary from -2 to 2, and then y is going to go from 0 to 6. And those are the 6 different ways that you can set up that in particular problem. Okay, and obviously, as you can tell, that took quite a long time just to get through that one. As a matter of fact, I'm probably going to stop this video after this problem, and then we'll pick up with the next one and see how long they take. But I really wanted to walk through that one slowly so I can give you an idea of what it is that you're thinking or what you should be seeing. So the biggest thing is you need to know the functions. You kind of need to know what the shapes look like 3-dimensionally to maybe give them a sketch. And then you've got to be able to see the projections visually as to what it would look like if you project something into one of the 3 planes, because you're going to have to be able to write all 6. All right, so I think we are going to come back with a second video because this one's going to be just about 20 minutes. The next one is a little bit harder to visualize, so I've actually done a couple things. I actually gave you a sketch as well as I'm going to put it into a three-dimensional manipulative that I can show you. All right, we'll come back with a second video.